to you the parts that you have to refer to. You can refer to for more details. Okay? So this is the sections that I explained to you, and behavior of imperfect column. So please read through this one. I already explained this. And this is the derivation process. The derivation process is you need to get the governing differential equation. For this, you can follow this derivation process. Then it will bring you to these equations. Okay. Then what do you do next? You change it into this standard form. Then there are two parts of the solution. So please go through this. There's a particular, which is complementary, and the particular solutions. And particular solutions, the complementary one, homogeneous one, which is on this side equal to 0, always like this. A sin kx is b cos kx. It's always in that form. Please refer to your notes. It's a bit not sharp here. It's always in this form plus some extra things. And this extra thing depends on this. What is the right-hand side of these equations? And for this case, when you have sine here, so what do you do? So this one explained to you. This is about a little bit on the mathematical part, how to solve the governing differential equations to get the particular solutions. And here, the explanation is given there. Please follow that thing. And finally, what we want to get is what is the particular solutions. The particular solutions is given by this particular equation here, and you add up with the homogeneous one. You add up with this, then you get the solution of this to these equations. Then there is A and B here. A and B here, class, you always need to use boundary conditions. You always need to use boundary conditions. So here we are using the boundary condition at x is equal to 0 and x is equal to L. What happened to the column? We use these boundary conditions, and finally we come to this conclusion. B will be 0 here, and A sin KL equal to 0. Okay, B0, so straightforward, we put B0 here, but then A sin KL equal to 0, we have to decide. If A is equal to 0, what happened? Then if sin KL is equal to 0, what happened? Which one we should use? So this is the explanation there. And finally, we come up to the conclusion that A cannot be 0. A 0. Okay. If A, here you get to the conclusion either A or sin KL must be 0. If we put KL is equal to 0, then the solution that we get is not what we want. And this is the meaning. If KL is equal to 0, then we get back the solution is equal to P is equal to P Euler. So this does not apply to this case. So from this, we conclude that A must be 0. So A 0, B 0. So the solution for Y remain only this part. So this is the explanation here. If you go to detail in that page. So as a result, A 0 and B 0, so we come up to the conclusion that the solution to these equations that we have is only the particular part here. Because A0, B0, we get to this. Then we add to the initial shape, then we get the final shape, which I already shared with you in the notes. Okay. So here I just want you to go to how is the derivation process. And here it is not clear here. Refer to your notes, please. Then the total deflection at mid height, which is from here, we put x is equal to L over 2. Then we get to these important equations that we can understand the behavior of a column. So if you go to the next page, then this is the diagram that I share with you. And here is the explanation of what happened. What we can understand from This diagram is explained here, and this is I already gone through. So it is good for you to go through again this particular sections. Okay. So next will be if we go to eccentrically loaded columns, another case of imperfect column. So the derivation process. Again, the derivation process here, we start with this, get to this, rearrange like this. Then there are always two solutions. The homogeneous one, always the same, a sine kx plus b cos kx, minus this one depends on what is on the right-hand side of the equations. Then the a and b must be decided always by using the boundary conditions. So we use the boundary condition for this column here. Then we decide, we found that b is equal to e and a is equal to this. So this is decided by using boundary conditions. What happened at x is equal to 0? What happened is x is equal to L. Then we get this, we substitute back, then you get the solution for y. So the solution for y is in this form, and here it want to change it into some form that is easy for us to interpret. So they rewrite these equations. They rewrite these equations by introducing, by first, again, substitute x is equal to L over 2 to get the mid-height deflections. You substitute x is equal to L over 2, you get these equations. And here, because there are a lot of this cos KL, sin KL, and then they make use of this identity, rewrite this equation, and then you can get into this form. Yeah. Or remember what is K, and we want to get this. We want to get these terms out. So here, this one we can rewrite to get this form. Here you can try here because you have secant K. K is square root P over EI. Okay, so you can rewrite this, which is coming from these equations. Consider this, you get this, then you rewrite into this form. Why we want to rewrite in this form? Because we want this thing appear. We want this thing appear here. P over P Euler, where P Euler is pi square EI over L square. So based on this, we plot the diagram that I shared with you on the first part of the lectures, this diagram. Okay. So after this, it explains again what happened, what can we understand from this diagram, and here it gives you some explanations about what I already summarized for you. Summarize for you what we can understand from the behavior of imperfect column. Okay. So please go through this. Okay. Now, what I want to explain here is this part here, which we can take that as another criteria. Yeah? Another criteria for the definition of P critical. And how do we apply that definitions? Yeah? So according to what we have the definitions of P critical, which is the load where neutral equilibrium is possible. Yeah. Neutral equilibrium means the concept class, we have this. If you disturb this and after disturb, it goes there, it will stay there. Okay. If you disturb this after disturbance, it will go to the neighboring one and stay there. Which means if the column, if this one is at a certain load, if you disturb it, then this column will bend. It can bend and it can stay there. So this is neutral equilibrium. It can have two possible. One participant. I saw his name just now, but just now he is not here. I don't see any people waiting here now. I saw his name just now. Maybe he's trying to reconnect again. Sarki, yeah? I don't see his name at this moment here. If you try to connect again, please let me know. Okay. Now, so another criteria that we can use is by using the behavior of imperfect column. For slightly bent, yeah. For slightly imperfect system, then in the beginning, when you apply loading, it will go deflection very small. Then at certain level, when the load is increasing, approaching P critical, you get increasing without bound. So this is the behavior of imperfect system. So we can set when this one approaching, when it become large, then we can set. So this is a approximation of the P critical. So this is another thing that we can get from the behavior of imperfect system to set our criteria of P critical as for slightly imperfect system when the load level where the deflections here increases a lot, we set that as the approximation of our P critical. So that is one of the main things that we can derive from the behavior of imperfect system. And imperfect system, you can have two ways. One is slightly bent. Okay. The other one is with eccentricity. Eccentricity. Okay. So either way, we can simulate. We can simulate imperfect system. So this slightly bent also, we call it crookedness. Crooked means it's not straight, yeah? Crooked means not straight. So what we can learn from here is if you want to estimate the P critical for a problem, let's say I have a problem and this I subject this this frame, multi-story frame is subjected to compression load. Now, this is a perfect system. This is perfect system, which means everything when you do simulations, yeah, your columns, everything straight, this coordinate, you give everything the perfectly very nice shape. But in order to use this criteria, what we can do is you simulate them, you disturb this shape, you disturb it, you don't make it, you make it imperfect, you disturb the shape. There are two ways you can disturb it. First, you assign or you specify some imperfection, okay, in shape. You give some imperfection in shape. Then you apply the loading. Then from there, from the behavior, from this criteria, you can estimate the P critical. So the first thing is you make it a little bit bent. Okay, you make it a bit bent. You don't make it straight, but you said my column is a little bit like this, like this, like this, like this. You give them some imperfections. The same thing here. Then you give them some imperfection like this. A small one, okay? A small one. You give only some slight imperfection only, because if you want to estimate P critical using this second criteria, you have to give only slight imperfections. Slight imperfection. So one way you can do is in the computer program, once we have this model, we disturb the shape. We disturb the shape. We purposely make the column bend slightly. Okay. Then if you do analysis, you do the analysis, then from the result, then you monitor one of the deflections here. Let's say you monitor the deflections of some parts of the structure. Then you plot the graph. You plot the graph here, delta versus P. You increase the load. Then according to this behavior, you are going to get, when the load is very small, when you do analysis, then you get delta increase, but very small. But at certain part, at certain range, then you get delta is very large. You're going to get delta very large here. This is by simulations, okay? You purposely give this shape, you disturb the shape, which should be perfect. But if you want to use this approach, then you have to assign some imperfections. And that imperfection must be very minor, very minor. Then you do analysis based on the disturbed shape. Then you try to get this result. You take one of the displacement. Then if you plot this result, so when the P is small, so it's going to be, this delta going to be small, just like the behavior here. But when the P is increasing more and more, suddenly at certain stage, you can see delta increasing more and more. So we can set this as our estimation of P critical. This is what we can learn from here. This is for simulation. In actual experiment, you don't have to simulate this. Actual experiment, you are going to get behavior like this because in the actual specimen, actual structure already imperfect. But this is in computer model. Computer model, you can model everything very perfectly, everything straight, very straight. But if you want to use this criteria, this is one of the way you disturb it, you make it imperfect. Then you plot a graph like this. You have to choose some of the deflection that you have to identify that. Then at the point where the P, when you increase further, suddenly deflection increase a lot. We take that as the P critical for this example. That is one way. The second way is, what you can do is, because you can apply also eccentricity. Yeah. The second thing is, the second possible way is you apply eccentricity. The same structure. The same structure. Okay. You apply eccentricity means I give this loading some eccentricity means I have a P. Then I apply some moment here, which I give them some PE, maybe P, and then here some PE here. So I purposely applied some eccentricity. I disturb it. So this is another way. Then again, you monitor one of the deflection at the top there again, you monitor. Then you plot the graph again. Then again, you are going to get your P, this eccentricity must not be applied too large. Too large, then you won't get a good estimation. Then suddenly you get increased again like this. So this will be the approximations of P critical for this using this approach, where you assign some imperfections. Okay. So here is assign some eccentricity. Okay. Apply some eccentricity of loading. Apply some eccentricity of loading to this example to simulate behavior of imperfect systems. So that is one way. The first way, as I explained just now, you assign some imperfections. But these imperfections or eccentricity must be small. Don't apply very large one. You apply very large one, you disturb too much, then you are going to get not very good behavior, not very good estimation of the P critical. And this is, we do this very often, okay, in order to find the P critical. But the difficulty here is how to apply these imperfections. The difficulty is how to apply these imperfections, okay? So there are some technique that we can choose how to apply these imperfections. So the imperfection that we can apply, okay, this is only for knowledge. We will not be able to cover that. If you are doing your research on buckling, we use the eigenvectors. Okay. We use the eigenvectors, which is the buckling mode. We use the possible buckling mode. We can do analysis. We can get the buckling mode. We can get the buckling mode, the possible buckling mode of these structures, and then we choose the one we choose. We have to make choice of the possible buckling mode. Then we use that as the imperfections. We use that as the imperfections. Okay. So let's say the eigenvector is given by this vector phi. Eigenvector is like your vibration mode. Eigenvector is like your vibration mode. It gives you the shape. And then you scale it, okay? Imperfection, you scale it with some small value alpha. With some small value alpha to get the imperfection that you want, then you superimpose on the structure to disturb it, okay? So the choice of this imperfection is very important if we want to use this method. If you use the wrong choice, you might not get the lowest buckling mode, you might get the higher buckling mode, the higher critical load. What we want is, we want to get the lowest critical load. So the choice of this imperfection is very important to be used. Okay. So this is what is being written there on that page that I would like you to take note of. Okay. So you say the critical load is the load at which the deformations please go through again here. The critical load is the load at which the deformation of a slightly imperfect system increase without bound. Increase without bound means increase a lot. Okay. To apply this criteria, okay, one gives the structural member or system to be investigated a small initial deformation. It must be small, okay, class, and then determine the load at which this deformation becomes unbounded. It becomes very large. So if you go through this is what I meant by that. When it increases a lot, then that is the criteria for critical load. So here mentioned again, another thing is that we can, important things that we can get from the discussion here is the behavior of imperfect system. You can simulate by giving imperfection in shape